What's up everyone, in today's video I'm going to show you guys how you can purify your own proteins and how you can practice this to create your own purification schemes. Now you can practice this with this site. What you're gonna want to do is hit start from beginning and complex mixture. Now you can choose any protein to practice on. I prepared protein 36 for you guys. So this is important. I know that its enzymatic activity is stable for several hours at 45 degrees and at pH values between 3.5 and 11. That's something I want to remember. Okay, let's start. So just to clarify everything, our goal is to purify protein 36 from a complex mixture of proteins. So now all of the protein 36 is still in the mixture, of course. We have so many milligrams of total protein, and here you can see the enrichment and the cost. So the first thing you can often do is a heat treatment. For example, well, we know our protein will denature or get unstable above 45 degrees. So 45 degrees itself was fine for several hours. So let's take 2 hours, for example. And let's see what happens. So as we can see, the yield remains 100% and the activity is not affected. While the mixture is 2.1 times purified, removing 501.6 milligrams of unwanted protein from the solution. Is already a nice, easy and cheap step. Now this mixture we can further purify based on its net charge and molecular weight. But first we have to do a 2D page to figure out which molecular weight and charge our protein has. These represent all the proteins in our solution. Here you can see the isoelectric point and the molecular weight on the y-axis. But we have no idea which protein of all of these is ours. So let's do an immunoblot, maybe that's better. Yeah, an immunoblot. And here we can see that this is our protein. So by doing an immunoblot, which is based on antibodies, the protein of interest can be identified in the SDS-PAGE gel. So from this we can conclude that the protein of interest has an isoelectric point around 7.8 and a molecular weight around 27 kilodaltons. Most of the other proteins in the mixture have a lower pI. So let's go back. Remember that this is our protein. From the immunoblot we know that this is our protein. And most of the other proteins in the mixture have an isoelectric point lower than it. This gives us the option to conduct a first separation in which we make use of this difference in net charge. And for this we can, for example, use an ion exchange chromatography. If the pH of the buffer is greater than the pI of the protein will be positively charged. If the pH of the buffer is less than the isoelectric point of the protein will be positively charged. Since the protein of interest has a pI around 7.8, using a buffer at pH 7 will give our protein a slightly positive charge. So let's hide the gel, go to separation, and I'm going to do an ion exchange chromatography. We know that all proteins with a pI lower or equal to 7 will be negatively charged when I set the pH to 7, or they will be neutral, that's also possible. And thereby we can separate all proteins with a pI lower than 7, which are most of the proteins in our crude mixture. I'm going to use a cation exchanger for this, because this is used to bind positively charged proteins and thus binds our protein of interest, protein 36. So all the negatively charged proteins will be washed away over the column. And to elute all the positively charged proteins bound to the resin, well, you can actually choose, but I'm going to use a high salt concentration, which we're going to add as a gradient from 0 to 0.5 will be fine probably. So 7 as I said, and then this is the obtained result. So from here, every peak represents a protein in the mixture which is still present after doing the ion exchange chromatography. So let's see which peak represents our protein by doing an enzymatic assay on it. Okay, so clearly this one with fraction. So fraction represents the solutions we got out of our ion exchange chromatography. So we have different Eppendorf tubes, for example, with different fractions. So we can discard all of these and discard all of these. Because we can see our protein is in fractions 51 to 65. So we keep these fractions, we pull them and use them for further purification. Okay, so let's pull our fractions. 51 about to 65. So now we can see the enzymatic activity of our protein has barely been changed through all the procedures. The yield is still 100%. We have enriched almost 8 times and got rid of a lot of contaminant proteins. Now, to go further, we knew from the SDS-PAGE, let's show it again. From the SDS-PAGE, you wouldn't really have to do another one, but this is just to show you guys. You can also deduce this from the first SDS-PAGE. We can see that there is also a big difference in molecular weight, which you can see here, between the remaining proteins. And as you can see from the ion exchange chromatography, all these proteins have been removed. So this mixture can be separated by example a gel filtration. So a gel filtration makes use of the differences in molecular weight between the proteins. Beads with pores of known sizes are used to retain proteins flowing through a column, and the bigger proteins can't enter the pores and will elute first from the column, while the smaller ones will be retained by the pores and elute at the end. So our protein has a molecular weight of about 28 kilodaltons. So separation, gel, let's first hide the gel, separation, gel filtration. I found out by trial and error that this is a pretty good one, which has a fractionation range between 12,000 and 130,000 kilodaltons, which you can see here in the info tabel. And our protein is well within this range, so it should be fine. Okay, so the result of this purification step can be seen here. And by performing another enzymatic activity assay, we can see that protein 36 is located in fractions 50 until about 65. So let's again pull these fractions. So I set 50 to 65. Okay. And we have another purification. Look how many proteins we have removed from the crude solution. We only have 80 milligrams left. We have enriched 52 times and our yield is still almost 100%. So we almost didn't lose any of our protein in the crude solution. Now to check the composition of the newly obtained protein mixture, the purified mixture we have now, we can do another 2D SDS-PAGE. And we can see that this is our protein, very present in the mixture, almost pure, but there is still one contaminant present, one other protein. Since it is clear that the difference in both pH and molecular weight between the two proteins is too small to be used as a base for another purification step, we can't really separate these proteins based on molecular weight because they're very similar and we just tried that and it wasn't possible. And based on isoelectric point, it's also very difficult to separate this. Therefore, for the final purification, to only get this protein in the solution, we are going to use a hydrophobic interaction chromatography, this one. So this technique is based on the difference in hydrophobic and hydrophilic properties of proteins. Now experimentally I found out that this one is better for our specific situation. The gradient is fine. So here we can see the result of this final purification step. Here we still can see that probably the big peak will be our protein. Indeed, so we're going to pull these fractions, which is about 45, let's say, to 60 is fine. So here we can see that only 12.8 milligrams of the total 959 milligrams of proteins is left in the solution. The yield is almost 100%, which means that almost none of the protein 36 was lost along all these steps. The activity almost didn't change either. And the crude extract is enriched with a factor of 75. Now the whole purification process took, when calculating with this, about 5 days, which is very normal. So overall, this is a very efficient and effective purification. Now to prove that only protein 36 is still present, indeed, here it is. This one is removed, all of these, do you remember the first SDS page? All of the proteins have been removed. So this is a beautiful example of a protein purification scheme you can obtain just by, well, in the beginning it will be lots of trial and error, but you will get better at it when you practice a lot. And you'll really get the feeling for it by just logic reasoning. So guys, I hope this video was helpful. Consider subscribing if you enjoy my videos or find them helpful, and I'll see you next time.